How much does a sewing needle weigh? Practically nothing. About a gram, maybe less. The kind you find tucked in the corner of your grandmother's spool of thread box? Pretty harmless. Now, imagine that same needle out in space, in absolute pitch-black emptiness. Imagine there's a cutting force pushing it, and it's being accelerated faster and faster until its speed becomes utterly insane. Say it's moving at 99.99999% of the speed of light, an almost comically large string of nines after the decimal. At that moment, it stops being an insignificant scrap of metal.
It becomes a cosmic bullet, a kinetic warhead. All of the energy of the most powerful nuclear bomb you can imagine squeezed into its sharpened tip. And its target is clear: Earth.
Ask most people what would happen if a sewing needle hit the planet at that speed, and they'll shrug. It'll make a little hole, right? A streak of light across the sky. If they watch too many superhero movies, they might even say it would pass straight through the other side of the planet. But that intuition is fundamentally wrong. The true outcome is far, far scarier. If this were to happen, you wouldn't get a neat little hole for someone to find. This is not a small puncture. It's a complete wipeout, an extinction event triggered by the least important object you can imagine. Let's see how physics turns a humble sewing needle into a planetary reset button.
First, a blunt but necessary scientific fact. According to Einstein's theory of special relativity, the backbone of modern physics, any object that has mass, like you, me, or that needle, can never actually reach the speed of light.
Why? Because the closer you get to light speed, the more energy is required to accelerate, and that required energy grows without bound. To reach light speed, you would need infinite energy. We don't have infinite energy, so reaching the speed of light is impossible. But we didn't come here to say it can't be done. We came to ask, what if it could? So we'll allow a little scientific cheating. We won't pretend the needle moves at light speed. Instead, it's hurtling at a crazily high fraction of it, the number I mentioned earlier, 99 point, with dozens or even 14 nines after the decimal. Those extra nines might look obsessive, but I promise you, those tiny differences after the decimal are what separate a dramatic sight in the sky from the end of the world.
Let's get back to our needle. A standard sewing needle, its weight is about 1 gram, totally harmless. But when we strap that 1 gram object onto that insane velocity we talked about, it isn't a needle anymore. It becomes a pure energy projectile wearing needle-shaped clothing. This is where the universe's most famous equation walks onto the stage. E equals mc squared.
That equation isn't just chalk on a blackboard. It's a fundamental law of the universe. It tells us that mass is a highly compressed form of energy. When an object moves at speeds close to light, its kinetic energy, the energy of motion, skyrockets. The precise formula for kinetic energy is K equals gamma minus 1 times mc squared. In that formula, gamma, the Lorentz factor, plays the starring role. As speed approaches the speed of light, gamma blows up toward infinity. For our hypothetical speed, gamma is roughly 70 million. Now plug that number into the formula. That 1 gram needle would be carrying kinetic energy on the order of 2 times 10 to the 17 joules. But that looks like a simple number, and by itself, it doesn't seem terribly scary, does it? So let me translate this for you. The atomic bomb dropped on Hiroshima released about 6.3 times 10 to the 13th joules of energy. By a back-of-the-envelope estimate, our needle would carry energy equivalent to more than 3,000 Hiroshima bombs. That's roughly comparable to the Tsar Bomba,
the most powerful hydrogen bomb in history. Yes, a 1-gram sewing needle in this thought experiment, packed with roughly the power of humanity's largest weapon. Now it's starting to get scary, right? Good, because all of this is the setup for sending our needle into Earth's atmosphere. From this point on, what happens is pure science fiction.
The needle rips through the air at its insane speed, but the air isn't empty. Every atom of the atmosphere, nitrogen, oxygen, stands as an immovable obstacle in its path. Each collision between the needle and those atoms is so energetic that the atoms are utterly destroyed. Electrons are stripped away, and a tunnel of ultra-hot plasma at millions of degrees forms in the needle's wake. Those collisions can even induce nuclear reactions and set off a chain reaction. Now, a crucial question arises. We said these impacts cause nuclear fission and trigger a chain reaction, but doesn't fission normally require special materials like uranium or plutonium? How can nitrogen or oxygen in the air be split? The answer is in one word: energy. In a conventional atomic bomb, we rely on heavy, unstable nuclei, like uranium-235, that will split easily when struck by a relatively slow neutron, releasing more neutrons and sustaining a chain reaction. But when you compress an amount of energy equivalent to thousands of nuclear blasts into the tip of a needle, you don't need unstable nuclei. The kinetic energy of the needle and the particles it slams into is so enormous that it can forcibly shatter even normally stable nuclei like nitrogen and oxygen. This process is called spallation, violent fragmentation. Our needle acts like a colossal hammer that pulverizes every atom in its way and pulls subatomic particles and energy out of them. So yes, before the needle even reaches the ground, a straight shaft of continuous nuclear explosions rips from space down to the planet. An apocalyptic, awe-inspiring sight, and the last view any living thing would ever see. But another important question remains. Why doesn't the needle just punch through the planet and come out the other side? Why does it explode? This question springs from a common misconception. We equate speed with penetrating power. A faster bullet usually penetrates deeper, and that's true up to a point. But at relativistic speeds, the rules change. The key, again, is that enormous energy. When the needle strikes the surface, or even collides with a single air molecule, in an extremely tiny fraction of a second, that kinetic energy must go somewhere. The amount of energy is so huge that it can't just be spent making a neat hole. The target material, dirt, rock, water, cannot absorb that energy fast enough. So the energy is released explosively and converted into other forms, light, heat, and a devastating mechanical shock wave. Imagine dropping a water droplet onto a scorching hot surface. Before the drop can wet the surface, it vaporizes with a sharp psh. Now imagine that droplet is our needle, and the hot surface is the entire planet. And that little psh becomes an explosion with the force of a tsar bomba. The needle and the first layers of the ground instantly turn into plasma. The explosion happens because the energy cannot diffuse fast enough, so it releases at a point and tears everything apart. Thus, the needle never gets the chance to burrow through. In the first femtoseconds of the impact, the needle and the surrounding material vanish into a blazing fireball. Okay, suppose we wanted the needle to actually travel through the whole Earth and exit the other side. How much energy would that require? To do that, the needle would have to travel roughly 12,742 kilometers through a path filled with trillions upon trillions of atoms of rock and molten metal in the planet's core. The energy required to cut a tunnel through all that material is astronomically large, unimaginable.
The energy we calculated earlier would be like a firecracker next to a nuclear bomb. It would be discharged completely in the first few meters of ground.
To punch through the entire planet, you'd need energy on the scale of super astronomical events, energy comparable to or exceeding the sun's total output over millions of years. So physically, passing straight through the Earth is even less possible than the initial impact itself.
So, back to our realistic scenario. Here's the short version. The explosion happens. A colossal fireball vaporizes everything for tens of kilometers. The blast wave, traveling faster than the speed of sound, sweeps across the planet and levels every structure in its path. Seismic waves, far beyond anything we've experienced, trigger tsunamis hundreds of meters high that swallow coastal civilizations. And then, silence.
Billions of tons of dust and ash are lofted into the atmosphere, darkening the skies for years. The sun disappears from view. A nuclear winter begins. Planetary temperatures plunge, plants die, food chains collapse. Earth enters a swift, merciless ice age. So what's our final answer? A 1-gram sewing needle hitting Earth at near light speed is not a little hole, it's a planetary reset. An extinction-level event that makes the dinosaurs look lucky. If you enjoy videos like this, don't forget to like and follow us, my friend. And if you have ideas, write them in the comments. Maybe we'll explore them in the next video.